Hello, we are Group and we're here to present our progress on LoveTR to the rescue, overcoming real raw texture environment challenge with advanced feature matching. This slide is table of contents. In this progress presentation, we summarize our previous announcement proposal presentation and introduce the latest SOTA feature matching method, LoveTR. Next, we will discuss our progress in applying LoveTR to past Rio, and finally, we will present our plan for the remaining period. At first, the revisiting proposal section. As we mentioned in our previous proposal presentation, past Rio showed that picture extraction performance is highly depends on environment. The video above show an experiment using past Rio to generate a map from sensor data obtained from a car driving over the bridge. As you can see, the system is obtained in accuracy driving direction for the bridge data. To address the challenge related to feature matching, previous work like past Rio 2 introduced an incremental KD3 data structure to enhance the picture extraction, acknowledging the impact of environment on this progress. However, our team proposed an alternative solution. Our approach involved leveraging the past Rio model but replacing the feature matching component with a method called LoveTR, based on detector-free local feature matching with transformer.
The second section is detailed explanation of LoveTR. I'd like to discuss local feature matching, a fundamental concept in computer vision that plays an important role in a variety of 3D computer vision tasks. These tasks include structure from motion, SFM, simultaneous localization and mapping, SLAM, and visual localization. In computer vision, local feature matching is the cornerstone of many 3D tasks. These tasks include understanding the 3D structure of an environment, or correctly determining the position and orientation of a camera, or recognizing the location of an object in an image. So, how do we perform local feature matching? It generally consists of three main steps. First is feature detection, second is feature description, and lastly, feature matching. First up is feature detection. In this step, we identify characteristic points or regions within an image. These points are selected based on their uniqueness and repeatability. For example, you can look for corners or other characteristic shapes in the image that can serve as reference points. Feature detection is followed by the feature description phase. In this step, we assign descriptors to the previously detected features. These descriptors create a unique signature for each feature, allowing it to be distinguished from each other. These descriptions play an important role in the matching process. The final step is feature matching, where the system matches features between two images. By establishing correspondence between the features, we can understand how the world changes between the two viewpoints. This is essential for tasks like SLAM, where we need to precisely track a camera's position and orientation. However, the problem with feature detectors is that they may not extract enough points of interest that repeat across images due to a variety of factors, including poor texture, repeating patterns, viewpoint changes, illumination changes, and motion blur, and so on. This problem is especially pronounced in areas with low texture or in indoor environments where repeating patterns dominate the field of view. Without repeatable points of interest, it is impossible to find accurate correspondences even with perfect descriptors. LoveTR achieves local feature matching by using an innovative method. It interleaves self and cross-attention layers multiple times. This process allows LoveTR to learn and utilize densely arranged globally consented matching pairs, similar to what we observe in ground truth matches. One of the remarkable aspects of LoveTR is its ability to produce high-quality matches even in challenging scenarios. Whether we are dealing with indistinctive regions, low-texture environments, motion blur, or repetitive patterns, LoveTR can still provide reliable and precise matches. LoveTR's approach includes a multi-level matching strategy. It starts by establishing pixel-wise dense matches at a coarse level, providing a broad overview of feature correspondences. Then it refines these matches at a fine level, focusing on maintaining the highest quality matches.
The third section is progress of LoveTR plus FastLeo. One of the key steps in our process is the transformation of 3D LiDAR point cloud data into 2D range image. This conversion is essential as it allows us to work with the data more efficiently. Once we've successfully converted the 3D LiDAR point cloud into a 2D range image, we move on to the feature matching phase. This is where we identify and match key features in the 2D image to achieve our objectives. However, LoveTR is designed to work with 2D images. This limitation necessitated the transformation of our 3D LiDAR data into 2D format. We envision that this conversion will allow us to utilize LoveTR's impressive capabilities and effectively accomplish our goals. After the feature extraction phase, we can get matched feature points in 2D space. In order to use them as LiDAR odometry, we needed to recover those 2D matched features into 3D LiDAR point clouds. Description of all these sequences are well shown on the slide. First, let's look over the feature matching progress we have done. To conduct our experiments with LoveTR, we utilized a specific set of tools and libraries. Our experiment environment was built on PyTorch, specifically version 1.8.1. Along with other essential packages like Cornea, OpenCV, and more, you can see the details in the figure on the slide. Now, let's talk about the heart of our experiment, the feature matching. We performed the feature matching on the Sejong 01 sequence of Murlan dataset using the trained weights for both indoor and outdoor scenarios. This dataset allowed us to test LoveTR's performance in various environments effectively. In our code, we implemented a feature matching process that extracts coordinates from the images. These coordinates serve as the basis for matching features between two images. This is a critical step in ensuring LoveTR's ability to provide high-quality matches even in challenging scenarios. In conclusion, our experimental environment for LoveTR involved a selection of key tools and libraries, while the feature matching process aimed to provide robust feature matching capabilities. First, we performed feature matching on the Sejong 01 data using outdoor weights. The first key issue we encountered is related to suboptimal results of the feature matching task due to mismatch between the model input size and the image size. This misalignment significantly hampers the effectiveness of our feature matching technique. We took this into account and used image resize to match the input size. After doing this, we found that the feature matching worked better than before, as shown in the demo video above. In fact, when applying the feature matching result to VestLeo, it is not possible to know whether the result is better for outdoor or indoor. In this regard, we have prepared a demo video with indoor weights like the above video. Now we need actual application of LoveTR into VestLeo framework. We started developing the source code. It consists of 4 parts. First, subscribe to LiDAR point clouds and make them into 2D range image. Second, run feature matching algorithm with range image and return matched feature point pairs in 2 dimension. Third, convert 2D feature matching pairs into 3D LiDAR point cloud. Now we completed replacing LOAM method into AI-based feature matching algorithm. Fourth, with matching points, calculate estimated odometry and plug in into VestLeo. You can check whole sequences with RQT graph on the slide. However, we had lack of time to plug in LoveTR into ROS visualizing process, and it was quite challenging. LoveTR was not aiming ROS real-time system. We had a lot to customize the code. What we mean is that we needed more time. Therefore, we decided to try another feature matching algorithm, such as superglue or ORB, and then we are thinking about comparing all the results among several feature matching algorithms. All we have to do is accept the best performance algorithm and analyze why it is the best. First, we tried superglue for feature matching algorithm. It worked really well. We used a pre-trained model which took training data for KT image data set. Top video is visualization of point cloud. Middle one is visualization of arrow connected feature matching pairs. Bottom one is range image. We got good matched features result. After this, we converted matched feature points into 3D point cloud. Result is shown on the right side of the video. Big size spear looking points are matching features. If you look close to it, you can see arrows connecting points. This should be the LiDAR odometry.
Finally, the future plan section. We are currently planning to replace the feature extraction part of VestLeo with LoveTR feature. In this progress, we need to conduct a comparative experiment to see which way to perform the best. In this process, we expect that The challenge will be to convert the image into 3D image without distortion or blur. Our ultimate goal is to make the SLAM algorithm work well in low texture environments like bridge and tunnel. And thank you.